on page 92, we have a couple, we have our box with our trig integration formulas and a couple more examples. So again, when we're doing a u sub, we're looking for that innermost function to be u. So in this example, u is x squared. If we take the derivative with respect to x and multiply by dx, we get du is 2x dx. So on in a problem like this where the constant multiple that's inside of the integrand already is not the constant that we want, here's how I deal with it. First, I would just kick the 3 out. So the constant multiple rule lets us put the 3 on the outside. So now we have x times the cosecant of x squared dx on the inside. We know we need a multiple of 2 on the inside, which means we need to divide by 2 on the outside. So I would do it like that in 2 steps. Just makes it a little easier to work with that fraction. All right, so now we've got our u, and we can identify within our integrand our du, and then 3/2, our constant multiple, is coming along for the ride. So 3/2 times the antiderivative of the cosecant of u du. And so our cosecant rule, we said we could do a very long substitution to derive it, or we could just memorize it, that the cosecant, the antiderivative, is -1 times the natural log of the absolute value of the cosecant of x plus the cotangent of x, and then all of that plus our constant of integration. Oops, but you know what? I made a mistake just now. Those should be u's, sorry. So the cosecant of u plus the cotangent of u. All right, so lastly, to substitute x back in, I'm going to give that negative to the 3/2. So -3/2 times the natural log of the absolute value of, let's see, the cosecant of x squared plus the cotangent of x squared, all of that in the absolute value bars, plus c, the constant of integration. All right, our last trig example, again, if we look for our innermost function, we're taking the tangent of e to the x. So e to the x is on the inside. We're going to let u be e to the x. So du is e to the x dx. This one works out nicely, where du is in our integrand, so we get the indefinite integral of the tangent of u du. And then when we take the antiderivative of that, we have negative natural log of the absolute value of the cosine of u plus c, our constant of integration. So our final answer would be negative natural log of the absolute value of the cosine of e to the x, all of that plus our constant of integration. All right, so for the trig integration formulas, again, you just need to memorize those. I would make flashcards and I would start doing it now because they're tough. So you want to make sure that you know all of those by heart. We do not want to have to derive them on a test or a quiz. All right, the last thing that we will do as far as u substitutions go, when a straightforward u substitution doesn't work, the last resort for our class is what's called a change of variable. And real fast, I want to point out that the reason we have to change variables really has to do with the form and the structure of both of these examples. So without doing any type of substitution, if we rewrite this as just the indefinite integral of x times the sum x plus 1 to the power of 1/2, here's the issue. We cannot distribute x over the binomial that has a power of 1/2. If it were x to the 1/2, like if the powers were switched, then we could do it, but we can only distribute over a binomial to the power of 1, or a trinomial, or just any polynomial. It's got to be to the power of 1. So the change of variable allows us to rewrite our integrand so that we can perform distribution, or at least that's in this particular instance. All right, it's going to start off just like a u sub. So we're going to let u be the innermost thing, which is x plus 1. So u is x plus 1. I'm still going to find du. Du is just 1 dx, so dx. But here's the trick. In addition to having u equal to x plus 1, we're going to solve this for x as well. So if we add 1, or sorry, not add 1, subtract 1, or add a negative 1 to both sides, we get that u minus 1 equals x. And we're going to use both of these equations. All right, so now if we rewrite our integrand, where I see x, I'm going to substitute u minus 1. Where I see x plus 1, I'm going to substitute u. And then lastly, our dx is just going to become a du. All right, so we've got now u minus 1. Since it's a binomial, I need to substitute it into parentheses. And then that's being multiplied with u to the 1/2 power. And then we said our dx is now du. So even though this rewrite doesn't look terribly different, what we can now do is we can distribute u to the 1/2 power to both terms in this binomial, because now u minus 1 is raised to the power of 1. All right, so now u to the 1/2 times u is u to the 3/2 power. U to the 1/2 times negative 1 is just negative u to the 1/2 power. All right, and now we just use the power rule to get the antiderivative. So I know I'm going to add 1 to my power and divide by my new power, my new exponent. And then we won't forget our constant of integration. And then lastly, we could substitute back in for u, x plus 1. So we have x plus 1 to the power of 5/2. And that's divided by 5/2, which is the same as times 2/5. And then minus x plus 1 to the power of 3/2 divided by 3/2, so times 2/3. And then all of that plus our constant of integration. Whoops. And make sure that your fraction bars are long enough that the entire numerator is on top. All right, the last example of a change of variable doesn't involve distribution, but in this example, our change of variable will allow us to what I sometimes call uncommon denominate. So right now, we have no way of rewriting x over x minus 4, because if the denominator is 2 terms, there's not much we could do about it. But if we had one term in the denominator and multiple terms in the numerator, we could break it up into multiple terms. So that's what this change of variable will allow us to do. So we need to let u be x minus 4, because if u equals x, that wouldn't help us at all. We'd just be stuck with the same problem. All right, so u is x minus 4. And then that means du is just 1 dx. And just like we did before, we're actually going to solve our u substitution equation for x as well by adding 4 to both sides. So u plus 4 equals x. All right, so that x we're going to replace with a u plus 4. Our x minus 4 we replace with u. And then our dx just becomes a du. So when we rewrite using the substitution, the numerator is now u plus 4. The denominator is now u. And we're multiplying by du. So the reason this helps us is now we could break up our integrand to be u over u plus 4 over u. And then we could simplify. U over u is just 1. And now when we find the antiderivative of 1 is just going to be u. 4 over u is 4 times the natural log of the absolute value of u, all of that plus c. And then lastly, well, almost lastly, we want to substitute x back in for u, or x minus 4 rather for u, and x for u plus 4 if we have a u plus 4. So we get x minus 4 plus 4 times the natural log of the absolute value of x minus 4, all of that plus c. But in our final answer, like if this were on a multiple choice test and we were looking for our solution, that negative 4 is going to go away. And here's why. Okay, we don't know what our constant of integration is. It's just a constant. It's just a number. So this negative 4, I could just factor that in to this constant of integration. That whatever this is, when I subtract 4 from it, I get this other constant of integration. So anytime we have like constants being added or subtracted in our antiderivative, we can just drop them if we're writing the antiderivative, because we'll always have our plus c to represent any unknown constant of integration. So the minus 4 is not necessary. All right, that's going to be it for integration rules and u substitutions.